So first, I'm Sharad Mehrotra. I'm also one of the faculty here. I work in data management area. While Pierre is setting up, adding a couple of extra things on top of what Alex said. The way the program is structured, and you'll quickly when you come here, you realize this. For a lot of you, the first 2 years is when you take your courses and so on. There are dual purposes to this. Obviously, you have to take your courses to get ready for your PhDs, but it also is a chance to explore essentially what your true passion is. It's understood by us that when you apply, I want to work in machine learning or AI or whatever, or bioinformatics or whatever it might be, or databases and so on, that's what you're thinking at that time. It's not necessarily required for you to kind of stick to that at all. You go explore what you want to work with, but the key question that we'll be monitoring would be, have you found an advisor or not? So you should, depending on if you're fixed in your mind, you know what you're going to do, great, do it. That's exactly what you should do, right? But if you want to explore a little bit and identify other topics and so on, you should feel absolutely welcome to do that as well. So there's no binding like that your contact is not just one faculty. The faculty is not admitting you, the department is admitting you. Okay? So you should explore, it's perfectly fine, it's natural and normal. Totally do that. So you keep that in mind. Second thing I think you should consider is as you go through the day-to-day, today is a very important day for quite a few. Some of you are local and they are from UCI itself, but a lot of you are not from here. Whatever questions you may have, try to make sure that they get answered for you, so you get closer to your decision-making point, essentially. So note down your questions, however silly or however simple, whatever it might be. Every question is a very, very valid question because it is the thing that will make the decision eventually for you, or you will make a decision based on those questions. Try to make sure that they get answered, okay, at some stage or the other. If it doesn't get answered and you think of the question on a return flight or whatever it is, send us email. We are really wanting you to come here, so we want to make sure that every question of yours is answered before you make your final decision. Okay, with that, Pierre is ready. So we have a first talk by Pierre Baldi, and Pierre will talk about deep learning and mining big data and so on. Pierre, I think joined us about maybe 10 years ago. Is that accurate?
16.
Oh, 60, oh, time flies. 16 years ago. And he started, he was the first person to have come in here and started bioinformatics. And one of the things for which UCI actually is now known is basically the bioinformatics area. Which applies, you'll soon find out what he does in terms of machine learning and mixing and using it for bioinformatics. We have one of the strongest institutes in genomics and bioinformatics, which Pierre basically heads. All right, so with that, Pierre, please.
Thank you, Sharad. Good morning. It's a pleasure to meet all of you. So I'm here representing the AI, machine learning, and bioinformatics component of this department. It's a very strong component. We have about 10 faculty members. And I'm going to show you a little bit the kinds of things we do in my group. So I'm not claiming that this is representative of all 10 faculty. I'm just going to focus on a few projects going on in my own group to give you a little bit of sense of the depth and the kinds of things we do. So broadly speaking, I'm interested in intelligence, in brains and machines, and it's very useful to compare both and to look at the similarities and the differences. If you look at the similarities between brains and machine, this is the Watson IBM supercomputer that won the Jeopardy game against human beings. If you look at what they have in common, there are a few things. For instance, they both use tiny electrical signals to send information between processing components. This is perhaps not too surprising. You couldn't compute using mechanical forces, for instance, or it would be way too slow, or sound waves, right? But the other great similarity between the two is the use of learning to achieve intelligent behavior, right? In fact, machine learning in computer science is one of the great success stories of computer science over the last 3 decades, is completely inspired from the brain, from biological learning. And today, you find machine learning everywhere. It's in your cell phones, it's used by Google, et cetera, et cetera, et cetera. So it has having a huge impact on society. And people are starting to worry that AI may take over, et cetera, et cetera. So it's a very important area, and the cutting edge of machine learning today, I would say, is deep learning. It's really creating a sort of revolution within the field of machine learning. And what is deep learning? It's not a new idea, actually. It's very old. It goes back at least to the 1980s. But the idea is that you're going to use neural networks, which are very simple computing systems where you have computing units that are capable of simple operations. They take a weighted sum of inputs and then pass this weighted sum through some nonlinear function, a sigmoidal function, a threshold gate, etc. And basically you get networks of this simple system where what you want to do, learning, is implemented by adjusting the weights. You adjust the weights of the network so that the input-output function of the network does something interesting to you. And typically you don't know what is the right input-output function, but you have examples, right? In computer vision, you want to recognize elephants in images. We don't really know how to do it, but we can certainly today create large data sets of images containing elephants and images that do not contain elephants, right? So use those to train these systems. And it's called deep learning because all the complex tasks you can think of, it is natural that, to think that you cannot solve them in a single step. You're not going to recognize elephants in a single step. You have to detect edges, you have to detect boundaries, etc. So it's a progressive process that occurs through many, many stages, and this gives rise to these so-called deep architectures, where you still have the same thing, weights between the layers, etc. And learning is how do you adjust the weights of such an architecture so that it has the right input-output function. When I give an image with an elephant, it produces, say, a probability 0.9 that there is an elephant in the image. Okay? I am sad to say that the best algorithm we have for training the weights is just gradient descent, stochastic gradient descent. So it is something that Newton could have done 3 centuries ago, but this is the best we have today. So I hope you will find better algorithm for training these systems, right? So anyway, this is what we have. And to show you why this is having an enormous impact, let me show you a benchmark data set, which is called ImageNet. Okay, this is a very large data set, 1 million images with 1,000 different categories. And people use this in conference, it's used to benchmark computer vision systems. And if you look at the performance, this is the error rate. In 2010, the error rate was around 27, 28%. Okay? Before that, it was flat for many years. People could not get better than 27%. And in just the last few years, using deep learning, the error rate has been going down tremendously. In fact, the latest point I have is now at 4.8%. Both Google and Microsoft have reached 4.8%, which is better than what humans can do at recognizing those categories in images. Okay? So it is a tremendous breakthrough. This is the example in computer vision, but if you look at the curves in speech recognition, natural language processing, you will see the same thing. At all the conferences, all the benchmark data sets, deep learning is winning easily. Okay? So we study deep learning. We study deep learning from a theoretical standpoint. We try to find better algorithms, etc., etc. There are many interesting algorithmic and theoretical questions around deep learning, but we also apply deep learning. And of course, you can apply it to these traditional problems, but I don't like to compete with Google. They have hundreds of machine learning PhDs, billions of computers, etc., etc. I'm not going to compete with them.
Is this mostly all based on gradient descent?
Yes. I mean, there is all kinds of new tricks you may have heard, dropout, etc. But at the bottom, the core is gradient descent, same algorithms that you had in the 1980s. It's called backpropagation.
Sure.
But it's the chain rule. I'm sorry to say Newton could have done it in an afternoon. Okay? But that's the best, the absolute best we have today, with a lot of tricks. So what has made, why in the 1980s we couldn't do this? I was a graduate student in the 80s, but we couldn't do this because number one, we didn't have the computer power that you have today. Number two, we didn't have the data. You didn't have 1 million images in 1980s. All this is brought about the internet, the sensors, crowdsourcing, all that, right? But today, big data is everywhere. So it's really a great time for doing deep learning. So what do I do to avoid competing with Google, Microsoft, Facebook, and all those guys? I go and look for problems in the natural sciences where those companies are not working at. So anything in physics, in chemistry, in biology is great for deep learning. There are very complex data sets, Very important problem both for science and for application. If you're interested in medical application, drug discovery, etc., there are incredible things that remain to be done just by applying deep learning in those areas. Okay? And a single group like my group can tackle all these problems. It's not that we're expert in every possible science in the world, but we can do that because we start from this common core of deep learning. The same people that are achieving state-of-the-art performance in computer vision have achieved state-of-the-art performance in speech recognition sometimes, because the technology is the same. Of course, you have to work with domain experts. And the beauty of UCI is that within walking distance, you have physics, chemistry, biology, School of Medicine. It's a very nice, compact campus with a circular shape. Everything is within walking distance. And that is incredibly useful for collaborations. So I have more collaborations with the other schools than within this building. Not because I don't like my colleagues, I love them, but it is natural for me to collaborate with physicists, chemists, and biologists, etc., etc. Okay? So let me show you a couple of examples. Applications to physics, okay? So high energy physics. By the way, Andrew Langford is a professor of physics here at UCI who was one of the director of the ATLAS consortium. That's a very large consortium of 5,000 physics labs working on this high energy physics, and is now advisor to the White House. So he's the main advisor in high energy physics to Obama. He's here at UCI. So what happens? These are the largest instruments humans have ever built. You have a tunnel underground in Switzerland, 16, 17 miles long, okay? And in this tunnel, you take protons and you accelerate them to speeds close to the speed of light. And then you smash them together, right? And this produces a firework of particles, of derived particles, which then arrive on the detector. So that's how the detector looks like. Okay? By the way, this is the size of a human. Okay, so it's a gigantic detector. It has 1 million elements collecting this shower of particles that comes from the collision. And the collisions occurs, millions of times per second. So this machine produces 1 petabyte per second, a gigantic amount of data coming out of the machine per second. Okay? So why do you do that? Why do you do these collisions? Well, in these collisions, you would like to detect whether there are so-called exotic particles. You may have read about the Higgs boson in the newspapers in the last 2 years, the discovery of the Higgs boson. There are thousands of so-called exotic particles that physicists are interested in. You cannot see in the current universe, but they may have existed, in the first 10 to the minus 15 seconds just after the Big Bang. So this is a little bit like recreating the Big Bang, having these very high energy collisions. These two protons, when they collide, they have the same energy than the TGV train in Europe. This is high-speed trains. And of course, these are tiny, tiny particles, right? This is another picture of the collider. You see, it's a gigantic machine, very complicated machine. And so we get the signals from the colliders after they have been filtered. So we don't get a petabyte per second, we get a little bit less. But we get these huge data sets, and we are asking, in this data set, was a Higgs boson produced or not? So it's a very simple classification problem. We have training examples of the background of the noise, collisions where there is no Higgs boson. We have example of collision with a Higgs boson. The simulators are very good. And so we train a deep learning system to predict whether Higgs boson was present or not. Up to now, physicists had used machine learning, but they had used shallow methods, things like SVM or shallow neural networks. And so this is an example of an experiment with a student of mine where just by using deep neural network, we can improve the detection by something like 8%. If you're familiar with classification problem, this is the area under the ROC curves, and we improve performance by 8%. This is the curve that we get with the deep neural networks. And this is what you get with shallow methods. Random methods would be aligned like this, right? So again, tremendous improvement just by applying deep learning to these data sets. So this work was done with Peter Sadowski, who is a graduate student in my group. You may meet him later today. Daniel Whiteson is a professor of physics here at UCI. Was published last summer in the top journal, Nature Communications. So that was a very nice piece of work. Second example, chemistry. How do you predict chemical reactions? So this is a little bit like natural language processing, but it's a strange language. You may have written equations like this when you were in high school. This is, for instance, the bromination of an alkene. An alkene has a double bond. This is HBr. It reacts with HBr. The bromine gets attached to the molecule. And you have seen those books of chemical reactions, gigantic books, and people study these all the time. But you have to realize that chemistry is extremely important. It's called the central science. It's very close to physics, to engineering, to medicine, pharmacology, etc. Everything we do in our lives is influenced by chemistry. You can look in this room, the carpet, the paint, your computer. Everything is dependent on chemistry and on understanding reactions. So being able to predict chemical reactions in the forward direction, backward direction is a fundamental problem in science, with many applications for synthesis, retrosynthesis, etc. So how do we build an expert system that can predict chemical reactions? Right, that's what you want to do. Well, one idea would be to try to write down the rules. Right, that's what you do when you study chemistry you take a class in, say, in organic chemistry. So we did that with a student of mine, Jonathan Chen. We wrote a system that has about 1,800 rules. There is a language for writing rules. It's called SMERGS. I won't go into the details, but this is the left-hand side of the equation. This tells you goes to the right-hand side. Each atom, this is carbon number 1, carbon number 2. You have to know where it goes in the second. You know, each atom, all atoms are conserved in a chemical reaction. There is nothing disappears. So you have to map each atom on the left-hand side to each atom on the right-hand side, etc. So you write this rule. Jonathan wrote 1,800 rules. It roughly covers undergraduate organic chemistry. And from this, we built a system that is interactive so that you can, learn interactively on a computer how to predict chemical reactions. So you have drills. It gives you the left-hand side. You have to predict the right-hand side, vice versa, etc., etc. Organized by topics. There is different subtopics. To make a long story short, this worked quite well. We started a company with UCI, and the company licensed this product, which is called Reaction Explorer, to Wiley. So now it's being distributed by Wiley worldwide. And that's also very nice. But there is a problem. The problem is that to maintain such a system is extreme. First of all, it's very tedious to write this. Okay, you have to learn to speak fluently this language. I mean, you're a computer scientist, you can do that. But you can see it's very hard to expand it. This covers only undergraduate organic chemistry. You want to start to cover a graduate organic chemistry or go into inorganic chemistry. You have to add rules. Every time you add a rule, there is a danger it may break the previous rules. And so it's very time-consuming and manual to expand this. Okay? So the question is, can we take a different approach to build an expert system that understands chemistry? And where, ultimately the goal is to be as good as a professor of chemistry, even better, right? Nobody has come even close to that standard so far. So what do we do? How do we use deep learning to try to tackle this problem? Well, if you look at the reaction I wrote there, this is the first molecule, the carbons are here, here's the double bond. It reacts with bromine, produces this product. The way chemists think about it, in a reaction, all you have is movement of electrons. The nuclei of the atoms don't change. You just have new electrons that are moving from some atoms to some other atoms. So, for instance, the HBr gives you H plus Br minus. The hydrogen loses its electron, which goes on the Br. Then the negatively charged Br attacks the double bond and connects to this carbon and produces this molecule, right? So all you have is movement of electrons from regions that are electron rich or sources to sinks, electron sinks, right? So the idea is very simple. Given the reactants, you're going to find all the sources, you're going to find all the sinks, and then you match all the possible sources with all the possible sinks. So you may have 10 sources and 10 sinks, you get 100 possible source-sink combinations. And the problem is you have to rank them. Which one is the most favorable? Which one is the most likely to occur when you put these two molecules together? Ranking is a machine learning problem. This is what Google does all the time. When you enter a query, you get a bunch of results. They are ranked, first page, second page, etc. So you can do ranking with deep learning, and that's exactly what we do. The problem is to get the data, so we use the previous system, the rule-based system, to generate data. We curate some data from the literature, etc., etc. But to make a long story short, we have a system based on deep learning, which we call now reaction predictor, which is currently roughly at the level of a graduate student in organic chemistry. And as we get more data, we should be able to improve it and hopefully reach the level of chemistry professors and then get even better. So that's the direction of this project. Now finally, here's an example from biology, which is the prediction of the structure of proteins. It's a very fundamental problem in computational biology. It's important for fundamental understanding of biological processes, but also for all kinds of medical applications. So what you have are proteins. Proteins, you can think of them as strings. These are polymers over a 20-letter alphabet, the 20 natural amino acids. And so these strings, they fold up in very complex 3D structures like this. And the structure is what matters for the activity of the protein. That determines whether this protein is going to bind to oxygen or to another protein or to DNA, etc., 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 right? So you want to predict the structure. You want to predict XYZ coordinates of each one of the atoms in the protein. Now, one big problem is that the structure of the protein does not depend on translation and rotation. If you move the protein around, the structure is the same, but the coordinates are changing all the time. So you have this fundamental invariance, and if you just train a deep neural network to go straight from the sequence to the XYZ coordinate, this is going to be a big problem. So the way we solve this problem is by breaking up the problem into essentially two main steps. In the first step, we use deep learning to predict features along the sequence. So there is things like, you don't see them very well, but alpha helices, beta strands, coil. Those are structural features that occur along the sequence. So you want to know where is the beginning of an alpha helix, for instance, where is the end of an alpha helix. On that little picture cartoon, the alpha helices are, I believe, in green. All the green stuff are alpha helices. These are places where the protein coils. There are strands, this is the blue stuff, etc. So we want to predict those features. And then from the sequence and the feature, we go to this thing called the contact map, which is a representation of the structure that does not depend on rotation and translation. So what is the contact map? It's simply a sparse matrix where in position I and J, you put a 1 if and only if the two corresponding letters are close to each other when the protein is folded. Okay? So it's a way of representing the structure up to mirror images. And you want to predict this sparse matrix. Of course, the diagonal, there is a lot of ones. Every amino acid is close to its neighbor, etc. So this part is not so interesting. What is really hard is to predict this corner. These are amino acids that are far away along the sequence, but they end up close to each other in 3D. And when you study language, it's the same thing. What makes all this problem difficult is when you have long-range interactions along sequences. They are somewhat sparse, but they are essential. Sometimes you have to go all the way to the end of a sentence to understand the beginning, right? It doesn't happen very often, but it's crucial. And that's what makes these problems very interesting and very difficult to solve. So the good news is that we have solved the first step. So prediction of this feature, secondary structure, etc., we are at about 95% correct. Okay? Just to give you a sense, in 1994, it was about 74% correct. So we have made good progress over the last 20 years or so. This step is essentially solved. The last step is also essentially solved. If you give me a good contact map, I can retrieve 3D coordinates. That has nothing to do with machine learning. It's a distance geometry problem. And so the really hard problem that is left to solve is this one. How do you predict the contact map? And there there is a benchmark data set, etc. The good news is that at a recent benchmark experiment or competition, deep learning got position 1 and 2 in this problem. These are former students of mine and current students. The bad news is that the accuracy is still very low. So we're about 20% accurate on the corner of the matrix where it's very difficult. So there is plenty of room for improvement, but it's also a very, very exciting area. And there is another area that I like a lot is applications in neuroscience and neurobiology, because in a sense you're closing the loop, right? All the machine learning stuff is inspired by the brain, and now we're using machine learning to analyze data that is coming from neuroscientists, maybe getting new inspiration for new algorithms, etc., etc. And I'm about done. In closing now, I want to say a few things about the differences between brains and computers, which are very important and also very inspiring. For instance, there is huge differences in the energy consumption. Your brain consumes about 20 to 40 watts. The IBM supercomputer consumes 85,000 watts. So brains are incredibly more efficient than computers. Carbon-based computing much more efficient than silicon-based computing. And this raises questions of why, and can we do something about it? And there is many reasons why. I don't have time to go into that. But one of the reasons is that the architecture is completely different. Okay? In your computers, you have memory, you have processing, and you have to shuttle things between the two, essentially. In the brain, storage and processing are completely intertwined. We don't really understand how it happens, but they are certainly completely intertwined. And the question of how the brain stores information, if you think about your telephone number, where is your telephone number stored in your brain? How does it store it? The first digit of your telephone number, right? That fundamental question, it's stored somewhere in your head, but we don't really understand in detail where and how. We have a lot of information about that. But so that's a fundamental question that needs to be solved, and I think in the coming decades there's going to be a lot of exciting progress in that direction, and perhaps ideas for building new computing systems that are more efficient and more brain-like, if you want, in some way. These are just some of the students, postdocs that have been in my group over the past 20 years or so. It's not an exhaustive list. I want you to notice how happy they are. I take absolutely no credit for that. I give them very hard problems, very hard deadlines, etc. But in spite of that, they go to the Grand Canyon, they play music, so they end up being fairly happy here at UCI. So I thank you very much for your attention, and if you have some questions, I'll try to address them. Thank you. Yes?
How long do you think the supremacy of deep learning will last, and what will be next?
That's a $1 million question, right? I think deep learning is here to stay. In fact, it was there in the 80s. I used it in the 90s, even when it was not so popular. So I don't think it's going to disappear. I don't think it's just a short-term fad. But there are interesting questions on the horizon. How do you combine symbolic system with deep learning? Do you replace with deep learning, or do you combine them together, etc., right? Think about how, suppose you want to do a machine learning system that does mathematics. Okay? That's super difficult. But you can take a somewhat narrow area of mathematics that is still challenging, something like auto-compute symbolic integrals, right? So you can generate a training set today. You can use Mathematica and produce 1 million examples of symbolic integrals, polynomials, exponential, etc., etc. Can we take that data set somehow and learn automatically how to compute integrals symbolically? That's a very interesting problem. Nobody has done, but it's totally, at least you could get started by producing the data set. So, and then you could try to learn either by a deep learning system, or you can do a symbolic system. You can do, there are methods for deriving grammars from data somehow, right? And how these two can be combined or compete, etc., is not clear. And I think that's one of the interesting edges in AI and machine learning and deep learning.
Okay.
Other million-dollar questions?
Do you do much collaboration with the ecology department?
I don't personally, but it's just the way it happened. Obviously issues of environment and conservation, etc., are very important. So I think there are, very interesting possibilities there. But my group has not collaborated directly with them so far.
Any other questions? Let's thank
Thank you.
Thank you very much.